Hello again. So glad you're sticking with us in this course. Welcome to another instructional video. And today we are going to be focusing our attention on molecular geometry. All that means is we're going to be looking at molecules and the basic structure, arrangement of that molecule using different models, different diagrams, and I'm going to walk you through the process of drawing these diagrams yourself. But first we're going to look at some models and see what those models can teach us. We've been spending a lot of time looking at naming molecules, naming compounds, and we're going to dive more into now the structure of those and looking at the structure of it to help us understand some of the properties. We talked earlier in a previous video about how important those valence electrons are, and that those valence electrons are the ones that are involved in either the transferring of electrons. Those are the ones that are transferred from one particle to another to form ions and then form ionic compounds, or the sharing. Those are the electrons that are shared in covalent compounds, covalent bonding. And that is going to result in certain properties. We also talked about electron configurations, and that those electron configurations are all similar for the families or groups, which are the columns on the periodic table. And that leads to certain chemical and physical properties. So we're going to examine a little bit more thoroughly the structure of these compounds as we look at a theory called VSEPR. VSEPR is just an abbreviation, and we're going to learn what that means and how it helps us draw and diagram a model for a potential model for the structure of molecules. So these, by the way, are two-dimensional diagrams. They're not three-dimensional. We're going to talk about how we can then go from a 2D drawing into a potential three-dimensional arrangement in a little bit. In Model 1 here, we have some diagrams that are called Lewis structures, named after a particular gentleman, Lewis, who developed this structure, this diagram, this method of drawing. And we are given the diagrams here and then told a little bit about the particular molecules, and then notice here we're going to try to determine a three-dimensional molecular shape. Okay? These diagrams are all two-dimensional. They're drawn on a flat piece of paper, but we want to take that drawing and eventually try to understand what the three-dimensional view or arrangement of that molecule would look like. Molecules are not flat. They are three-dimensional. They live in the 3D world. And so that's what we want to get to eventually. Okay? This is really some neat stuff here, because obviously you can't see molecules, but we're able to, knowing properties of electrons and properties of different molecules and how they bond, how they arrange themselves, we are able to predict the actual arrangement of these molecules, and it's kind of neat to be able to do this. So let's look at Model 1 here and begin to answer some of these questions. Question number 1 says, name the type of structures shown in the left-hand column of Model 1. So we're up to go back up to Model 1, and we're looking at the left-hand column. Left-hand column, these structures are called Lewis structures. Okay, again, named after the gentleman who designed these and started to work with these. So these are called Lewis structures. You're going to hear this a lot, so just become comfortable with the name Lewis structures. Examine the drawings in Model 1. What does a solid line between two element symbols represent in the drawings? So a solid line here. This is a solid line here. Here's two solid lines. There's a solid line. All of these solid lines here are going to represent a bond. Those are going to represent actually a shared pair of electrons. So you'll notice here we've got for H2CO, if we study this diagram right here, we've got carbon as your central atom. We've got it bonded with hydrogen and another hydrogen, H2, and it's also bonded with an oxygen. So carbon in the middle and it says here that we have 3 bonding domains. Domains just mean where you would find a concentration of electrons. Electrons that are shared are going to be between the 2 atoms. And by the way, we are only showing the valence electrons. Those are the only ones we're concerned about because those are the ones that are involved in the bonding, either covalently in this case, or ionic compounds. But right now we're focusing on covalently bonded electrons. So we have 3 bonding regions. 1, 2, 3, and as a result, these lines right here are telling us how many bonds there are. Each segment here, if you see, each one of these are representing 2 shared electrons. So this would represent 2, that represents 2, that represents 2 that are being shared between 2 nuclei. So the solid line represents a bond using 2 shared electrons. What subatomic particles, either protons, neutrons, or electrons, make up these solid lines? These are electrons. As I already mentioned, those are 2 shared electrons. What does a pair of dots represent? A pair of dots, we have a little note for us down here. 2 dots mean lone pair. It means you have 2 electrons, we have to represent them, but they're not involved in the bonding. They're not being shared and they're not involved in the bonding. So 2 dots, or a pair of dots, is a pair of lone electrons. What subatomic particle, again, make up each dot? These are electrons. Domain just means, for us, it's just going to be a region or an area. Okay? Which molecules in Model 1 have 4 electron domains? Circle or highlight the 4 electron domains in the Lewis structure for each molecule that you identify. So we're looking for 4 electron domains here. As we analyze this model a little bit more, let's dive into it. You are given the formula, you're given a diagram, and then you're told about the areas of concentrated electron regions. Those are your domains, areas where there are a concentration of electrons. And we'll get to the 3D shape in just a second. So around the central atom, you always are talking about these domains and the bonds around the central atom. You focus on the central atom. In this case here, it's carbon. There are 1, 2, 3 electron domains around the central atom. In this case here, we've got 1, 2 electron domains around the central atom. Here we've got 4. Here's our 4. 1, 2, 3, 4 electron domains around the central atom. Here we have 1, 2, 3, 4. We have 4 electron domains. Notice the difference between number 3 and number 4. Here we have 4 electron domains. Each of those are a bond. Each of those are a bond. Here we've got 4 electron domains, but only 3 are bonds, and one of them is just a lone pair of electrons. I'll show you how we develop that in a little bit. Here we have 1, 2, 3, 4 electron domains. Again, 2 of them are bonds, 2 are just pairs of lone electrons. And here around the central atom of carbon, we only have 2 electron domains. I know this is a double bond, but that only counts as 1 electron domain, one region where there's a concentration of electrons. Okay? Which molecules in Model 1 have 2 electron domains? Circle or highlight the 2 electron domains in the structure for each molecule that you identify. And down here it says which one has 3. Well, we've already kind of gone through each one of those, and I pointed out which ones have 2, 3, or 4. Okay? When determining the number of electron domains in a Lewis structure, which of the following should you count? Find evidence from Model 1. So, we are going to focus on the central atom. We're not going to worry about what they're called peripheral atoms, the atoms around or outside the central atom. So I know for sure this is not going to be an answer. I don't count lone pairs that are around atoms that are not the central atom. If I'm determining the number of electron domains, I am going to focus on bonds or lone pairs around the center atom. Okay? I don't count the total number of atoms. I don't count the lone pairs that are on the atoms outside of the central atom. When determining the number of electron domains in a Lewis structure, do you count double bonds as one domain or two domain? I kind of already mentioned this. Double bonds is only one domain, even though, for example, as I pointed out here, this is a double bond right here. You only are going to count that as one electron domain. And this is going to become more and more clear to you as I actually step you through the process of you being able to draw these Lewis structures by yourself. Explain the difference between a bonding electron domain and a non-bonding electron domain using examples in Model 1. A bonding electron domain, these would be ones that are shared. Non-bonding, these are not shared. So the bonding electron domain means that you have electrons that are being attracted to and held on by both atoms that are being bonded. Here, you have non-bonding electrons. Those non-bonding electrons spend most of the time just around one atom, not being shared between two atoms, not being shared between two nuclei. Circle the correct word or phrase to complete the sentences. Pairs of electrons. What do electrons do? Well, electrons are negatively charged. So if you have two of them, or even if you have pairs of them, they are going to repel each other. Like charges repel. So electrons are going to try to push away from each other. That's going to be important to remember as we look at our theory, which is called the VSEPR theory. You're going to see how this is developed in a little bit. Pairs of electrons will repel each other. Two bonds on the same electron will try to get, well, if bonds are a result of electrons being shared, those bonds are going to try to push far away from each other. So if you'll notice up here, when these diagrams are drawn, they don't smash these bonds really close to each other. For example, this is not carbon and then four hydrogens. The four hydrogens that are bonded to carbon real close to each other, they spread out. They're going to spread out around this central atom. And you're going to see that this two-dimensional diagram actually, since it's flat, drawn on a piece of paper, it's not distributed around the central atom with 90 degrees, like on a flat piece of paper. We're going to see it actually go three-dimensional. And we'll see how the VSEPR theory helps us figure that out. All right. A lone pair of electrons and a bonded pair of electrons, same thing, they're going to push away from each other. All of these electron domain regions, these densities, they're always going to try to push away from each other. They're going to be held in by the central atom. They're still going to be attracted to the central atom, but around that central atom, they're going to spread out. They're going to spread out around that central atom as much as they can. Here's where we get to the theory. So, the VSEPR theory, that stands for valence. So valence would be the valence electrons. Shell, meaning energy levels, the outermost energy level where those valence electrons are. Electrons, we obviously are talking about electrons. Pair, electrons are going to be in pairs. If you think all the way back to a previous video where we talked about electron configurations and orbitals, orbitals are filled with 2 electrons each. That's when they're full. And then if there's more electrons, they got to go to another orbital. So we're talking about pairs of electrons. Electrons are usually found in pairs. And if you remember we draw, when we're filling those orbitals in the orbital diagram, remember we put one arrow up and one arrow down because the electrons are believed to spin in opposite directions in order to occupy a particular orbital. So we have pair and repulsion because electrons are going to repel each other because they have the same charge, both negatively charged. So the valence shell electron pair repulsion theory, VSEPR, and then we just kind of say it all together, VSEPR theory, helps us predict the shapes of molecules and is based on the premise, the idea, that electrons around a central atom repel each other. They're going to push away from each other while still being connected to that central atom. These electron domains are areas of high electron density, such as bonds. That could be a single, double, or even triple bond. All of these count as one electron region. A single bond is an electron domain. A double bond is just one electron domain. Even a triple bond is one electron domain. And lone pairs count as an electron domain. If they're not involved in bonding, a lone pair is still counted as an electron domain around the central atom. In simple terms, VSEPR means that all electron bonding domains and electron non-bonding domains around a central atom need to be positioned as far apart as possible in three-dimensional space. So we're going to have these spread out in three-dimensional space around the central atom. The theory specifies valence shell electrons. Explain why these are the most critical electrons for determining molecular shape based on your exploration of Model 1. Well, the valence shell just means the highest energy level, or the outermost energy level where there are electrons, because those are the ones involved in bonding. The valence shell, where there are those valence electrons involved in bonding. Okay? In the valence shell, in the VSEPR theory, what is repelling what? So we have electrons repelling electrons, as mentioned. Based on the information in the Read This section, which we just looked at, sketch one of the molecular shapes shown below in each of the boxes provided in Model 1. So, here's what we're going to do. We are going to take these given three-dimensional molecular shapes. They're giving them to you. These are possible three-dimensional shapes, and we're going to try to match them up here in Model 1 and try to figure out, which one of these Lewis structures would then translate to which of those 3D molecular shapes that are given to us. We're going to analyze the two-dimensional Lewis structures. Keep in mind the VSEPR theory that these electron regions have to spread out around the central atom, and then see how that leads us to a particular 3D molecular shape. Let's look at our possibilities. What I'm going to do is I'm going to take a particular 3D shape, look at it, and try to match it to one of the two-dimensional Lewis structures up there. What I see here is I have a central atom. I don't know what it is, it's just a central atom. There's our central atom. Then I've got atoms that are around that central atom. And I then have these bonds. Well, those bonds are representing shared pairs of electrons. So this might be a pair of electrons right here. This might be a pair of electrons. Since there's only one line there, could represent just a single, but it could be a double or triple bond as well. But I just know that there are electrons here in this area. Probably is going to be multiple bonds, as you'll see later on. But this is where electrons are being shared in between the two atoms, in between the two nuclei. So I'm looking for a central atom that has 1, 2 electron domains around it, and that's it. If there are only 2 domains, those 2 domains are going to try to get away from each other. while still being held to the central atom? Well, if they're trying to get away from each other, then while still being connected to the central atom, the most logical arrangement then is going to be that they go on either side of the central atom and form an angle between them of 180 degrees. So let's look back up at Model 1. Where does this happen? It happens in number 6. Notice double bond and double bond, but these only count as 1, 2 electron regions around our central atom of carbon, and as a result, this would be a linear arrangement. Okay? CO2, double bond, double bond. I'm not drawing the lone pairs of oxygen here. I can. This is going to be the three-dimensional model for CO2, and we realize that after drawing the Lewis structure, which I'm going to show you how to do, and this is a linear arrangement, a linear 3D model. Let's see if we have any others. Here we go. Number 2, I look at the central atom. Around that central atom, I have 2 electron domains. 2 electron domains mean that I'm going to have a linear arrangement with 180 degrees is our degree measurement between the bonds around the boron, around the central atom. This is linear. This is called the linear 3D shape. I'm not drawing the lone pairs. Okay? So those are our 2 linear ones. Let's grab another one here. Let's grab trigonal planar. Now planar means it is flat, and it's going to be in the shape kind of a triangle. So trigonal planar. By the way, linear also is could be drawn flat. Right? The other 3 you'll see are very much three-dimensional. So trigonal planar, what do we need to have a trigonal planar molecular shape? Our central atom here is going to have 1, 2, 3 electron domains around it. And the angle between each of these electron regions, and also the angle between the peripheral atoms, would be 120 degrees. Why 120? Because 360 divided by 3 is going to give us 120. This is divided equally around the central atom. So I'm looking for 1, 2, 3 electron domains. Let's see if we have any of those up here in Model 1. Here we go, our first one. We have 3 electron domains around this carbon. So this would be carbon double bonded with this oxygen up here, bonded with this hydrogen, and bonded with this hydrogen. Notice that this Lewis structure, I wasn't concerned about where I would place these electron regions. They're actually drawn kind of at 90 degrees, and this one looks like it's 180 degrees, but in reality it's not. You have to remember that this is a two-dimensional Lewis structure, and we are now going to have that lead us to a 3D shape, knowing that these electron regions are not going to stay close to each other. They're going to push far away from each other as far as possible and spread out as much as they can, taking up all the space around the central atom. That's why this is going to be 120 degrees, not 90, not 180. They're going to spread out equally around that central atom. So this 3D molecular shape for H2CO is going to be trigonal planar. Alright, we got a few more. Right here, let's look at these 3. We've got tetra, 4 hedral. Those are 4 kind of sided shape here. So we've got 4 regions around our central atom, and if they're going to spread out around your central atom, we're going to have an angle between those regions of 109.5. Let's see if we have any that are tetrahedral. Now, realize that what we have here is we've got 1, 2, 3, 4 bonds. I need a central atom that has 4 bonds around it. Okay? Look at the difference over here. This also has 4 regions around it, but one of the regions is a lone pair. Therefore, the shape of this molecule is determined by the atoms. This lone pair up here is not contributing, if you will, to the shape of it. It is pushing these other electron domains down. All right, it's taking up space. In fact, it takes up more space than a bonded region, but it's not part of the structure. There's no atom up here with this lone pair. So this has 4 regions, but only 3 pairs. It's going to have a different shape. It looks more like a pyramid if you just focus on the atoms. Here we've got 4 electron domains as well, but 2 of them are pairs, lone pairs. And as a result, those 2 pairs are going to take up space. They're going to push the other areas away from them, and you're going to have bonds down here instead of linear. Yes, this only has 2 atoms, 1, 2 bonded to the central atom, but it's not going to be linear. Why? Because these regions, these electron regions, are going to take up space and push these bonded regions away from them, causing a bent shape with 104.5 degrees between them. So I just want to point out that these next 3 all have 4 electron regions. But this one has all 4 are bonds. Here, this has 3 bonds, 1 lone pair. This one has 2 bonds and 2 lone pair. That's why it results in different shapes of the molecule. The atoms, the shape of the atoms, how the atoms are arranged around that central atom. Okay, so let's find a tetrahedral shape. I need central atom that has 4 bonds around it. 4 bonds. That would be our CH4 for sure. Right here, CH4. So here's our carbon. And then it's kind of hard to draw, but you kind of have to think 3-dimensional here. There's our carbon with 4 hydrogens around it, and this is your tetrahedra. Okay? Let's find the other one that has 4 regions, but it's going to have a single lone pair. 4 electron regions, 3 bonds, 1 non-bonding. So this NH3 here, and you've got a pair of electrons up here that are going to push those bonded regions down, and you're going to have kind of 3 legs, almost like a stool, and you're going to have your hydrogens like this. This is your pyramidal. Okay? Looks like a pyramid. And then we've got another one here that has 4 regions but only 2 bonds and 2 lone pairs. This is going to result in, here's our oxygen. This is, you got to know this is water, by the way. You have to know that water is bent and that the diagram is drawn like this. You would think that it only has 2 hydrogens, so you think, oh, well, I'm going to put a hydrogen on either side of it and make it linear. No, that's not the case, because these lone pairs here are going to take up space and it's going to push those bonds of the hydrogen down, and we're going to have bonds here with the 2 hydrogens resulting in what's a bent shape. You're not going to have linear, you're now going to have an angle between those bonds greater than 180 degrees, or here it's going to be less than 180 degrees on this side, okay, but it's bent. This is bent shape, sometimes called, I think maybe seesaw, or maybe that's a linear, it's called seesaw, but in any case, a bent shape is going to be as a result of having these lone pairs up here, even though you only have 2 bonds. Notice the difference between these two. Here's a good comparison, bent versus linear. It's linear because the only electron regions are bonds around, there's 2 electron regions and they're all bonds around the central atom. Here we have 2 bonds as well, but you've got lone pairs that are taking up space. Okay, so make sure you understand the difference between these 2 3D models. Alright, moving on, those are 5 that are very, very common that you should know, 5 3-dimensional molecular shapes. Alright, Often we draw Lewis structures with 90-degree bond angles. Do any of the molecular shapes in Model 1 have 90-degree bond angles? Yes, there are some that do, and they're not here, okay, but there are some that have 90-degree angles involved in them. But their point here is that our diagrams, while drawn on a flat piece of paper, we may make 90-degree angles, but when they are in reality, in real life, when they're three-dimensional and they spread out around that central angle, they're not necessarily going to be clear, distinct right angles. They're going to spread around that central angle, forming angles like 180, 120, 104.5, 107, 109.5. Okay, so it's not as clear cut as just 90-degree angles. But there are some three-dimensional shapes that are going to produce 90-degree angles. We just haven't mentioned them here. All right. Are the bond angles in the three-dimensional molecules generally larger or smaller than those shown in Lewis structures drawn on notebook paper? So the bond angles here, again, all they're getting at, when you draw it on a flat piece of paper, because we're limited to 2 dimensions, we draw it often at 90-degree angles here, okay? But in reality, we've got more space than on a flat piece of paper. We allow these electron regions to spread around a three-dimensional area, okay? That's all they're getting at here. So their point is that these actual angles are probably going to be greater than the 90-degree angles that we often draw on a flat piece of paper. So why is it are we able to get larger angles? Because we're going from a 2D flat structure, flat diagram, where we're restricted, and we're actually trying to now imagine these in the 3D world. And so we have more space. As a result, we have more space for these to spread out. So our angles are actually going to be greater than the 90-degree angles that we draw on a flat piece of paper. Identify the 3 molecules shown in Model 1 that have 4 electron domains each. What happens to the size of the bond angle in a molecule as the number of lone pairs on the central atom increases? So let's go back up to these 3 right here. If you've got 4 bonds, 109.5 degrees between each of the electron regions. If you've only got 3 bonds and 1 lone pair, 107. If you've got 2 bonds and 2 lone pairs, 104. And this is just going back to what I mentioned before, that these electron pairs actually take up more space. They repel more than a bond does. So this electron pair and these 2 electron pairs are going to push those bonds further away. They're going to need a little more elbow room, okay? And as a result, this angle decreases between the bonds. Here, the angle between the bonds is 109.5, but now because of that lone pair, the angle between the bonds is just 107. Here, 2 lone pairs, it even goes down to 104.5. That's the point. Lone pairs take up a lot of space, more than the bonds. Discuss in your group some possible explanations for the trend in Part A. Your presenter, okay. My point I already made is that lone pairs occupy more space than bonds, than bond regions. Okay? A student does not waste his time drawing a Lewis structure before determining the shape of PF3. The student thinks that the shape of PF3 must be trigonoplanar because there are 3 fluorine atoms bonded to the central phosphorus atom. So, it says draw the Lewis structure of PF3. I'm going to show you now the steps that you are going to have to follow in order to draw the correct Lewis structure for any molecule. Okay? And as I do so, You can write these steps down, practice them yourself, and become very proficient at drawing Lewis structures. First thing you're going to want to do is you are going to determine or count total number of valence electrons. Okay? So I have phosphorus, I have 1 phosphorus, I have 3 fluorine, and if we look on the periodic table, let me pull up the periodic table here. So here we have our periodic table, and in order to count the number of valence electrons, we need to remind ourselves that each of these elements are located in a particular group or family. Remember from a previous video that this group 1 here, the valence electron, the outermost electron, remember, is in the s1 orbital. So like, for example, lithium, it would be, this outermost electron would be 2s1. So it has 1 valence electron. Beryllium would be 2s2, would be the ending part of our electron configuration. So it has 2 valence electrons. I jump way over here to boron. This would be, the ending part would be 2s2, 2p1. So it has 2 and 1. It has 3 valence electrons. So you just count right across. It's very easy. 1, everybody in group 1 has 1 valence electron. Everybody in group 2 has 2 valence electrons. Everybody here has 3 valence electrons. Carbon's got 4 valence electrons because it ends in 2s2, 2p2. Everybody here, nitrogen, 5 valence electrons, 6, 7, and noble gases all have 8. So you just count straight across. We're going to ignore these transition elements just for a little while. Okay? We're going to just look at the main group of elements on the periodic table. 1, 2, jump over here, 3, 4, 5, 6, 7. That's what we need to focus on right now. Okay? So let's go back to our questions here. We're going to look at phosphorus and fluorine. I need 1 phosphorus and 3 fluorine, and I need to determine how many valence electrons do I have total. Phosphorus is here in the nitrogen group, 5 valence electrons. Fluorine is here in the halogen group, 7 valence electrons. So let's count those all up. 5, 3 times 7. 3 times 7. 7 valence electrons for each, and I've got 3 of them. So I have a total of 5 plus 21. I need to represent 26 electrons in my Lewis structure. You are going to then next create what is called the skeleton structure. The skeleton structure is basically taking the first atom, putting it in the central, and then making a bond with each of the other atoms in the formula. I've got 3 fluorines, so I'm just going to create a bond with each of those. Okay? That's called the skeleton. Central atom, bond it with each of the remaining 3 atoms. Then we are going to calculate the remaining valence electrons that we have to represent. What I mean by that is this bond right there represents 2 electrons. This bond represents 2 shared electrons. This bond represents 2 shared electrons. So far I have 6 that are shown. I have 6 in my skeleton structure. But I need 26. So now I'm going to determine 26 minus 6. I need to draw 20 more. And how do I do that? I use dots, pairs of dots. Fourth step. Fourth step is begin to populate each atom until it is full. And by full, what I mean is until it has 8 electrons, 4 pairs around it. And we're going to arrange them on top, bottom, right, and left, like a box around each atom's formula symbol. Why do they want 8? Well, 8 is more stable, kind of like the noble gases. The noble gases have 8 valence electrons. They're very stable, and as a result, the reason why these atoms form compounds and they form bonds is because by sharing electrons, they are going to be more stable, having a full outer valence shell. Okay? So populate each atom until to get what's called an octet. An octet around each atom. We're going to start on the peripheral atoms, the outside atoms first. So I need to show 20 more. So I'm just going to start. I already have a pair here around fluorine, so I'm going to put one more pair, and one more pair. Now fluorine's got 8. 2, 4, 6, 8. Remember this bond right here counts as 2. That counts as 2. 2, 4, 6, 8. Fluorine is happy. It's got its octet. So remember, I'm trying to get 20 more. There's 2, 4, 6, 8, 10, 12. That fluorine's happy. 14, 16, 18. That fluorine is happy. All the fluorines are happy because they got their octet. But I haven't drawn my total 20 yet. So where does the last pair go? It goes around the central atom. Is the phosphorus happy now? Yes. 2, 4, 6, and that lone pair give it 8 as well. Everybody has their octet. Everybody has a full outer valence shell, and they're more stable as a result being in this compound than if they were by themselves. So back to our question, the student thinks, oh, well, I don't need to draw the Lewis structure because it's got 3 bonds around it, must be trigonal planar. No, it has this lone pair. This lone pair, as we see right here, is going to push those bonds down and cause the shape to be pyramidal, not trigonal planar. Okay? So, oops, sorry. So that's what happens. That's why it's crucial to draw the Lewis structures, because you have to identify if there are any lone pairs that's going to kind of alter the structure of the molecule. Okay? So he thought it was going to be trigonal planar. He was wrong. No, he was not correct. It should actually be pyramidal. So as mentioned, you got to draw the Lewis structure because you also have to identify lone pairs. And as you'll see also, it is going to help us identify multiple bonds. So it's going to help us identify double or triple bonds, as you'll see in a little bit. Okay, this is going to take a little time here, but this is really, really crucial. I know this is going to be a little bit of a longer video, but this is taking time in order to build something that we are going to be using later on. So everything that we're doing, we are doing it so that we can build upon it and we can move forward. The better you understand this now, the easier later topics are going to be for you. Alright, let's look at H2S. And I'm going to follow my steps as I go through each of these. I'm going to draw all the Lewis structures, and then we're going to go back and do the 3D drawing, and then name it and talk about bond angle. But I think I'm going to go and do each of the Lewis structures just so you can see the repetition of all the steps and see how it all works. Okay? So, Lewis structure of H2S. I'm going to count my valence electrons. I've got 2 hydrogen and 1 sulfur. If I go to my periodic table here, sulfur is in the oxygen group. It's got 6 valence electrons. Hydrogen is in group 1. It has 1 valence electron. Okay? So I have one for each hydrogen. So that's going to be 2 valence electrons. Sulfur has 6, just like oxygen. So I need a total of 8 valence electrons drawn. I draw my skeleton structure. Now in this case, the hydrogen is drawn first, but it wouldn't make sense to put one of these as your central atom because there's 2 of them. So actually our sulfur is going to be our central atom. Kind of like water, H2O, okay? And then I'm going to draw my bond, my skeleton structure. And it doesn't matter if you get the angle correct here with your Lewis structure. That's not important. We're going to worry about that later on when we consider 3D and we look at the VSEPR. So Lewis structure, you can put these bonds anywhere you want to around the central atom. So I'm going to have an H on either side. That's basically my skeleton structure. Now I have a bond, another bond, that takes care of 4 electrons. Why? Each bond counts as 2. So there's 2, 4, I need a total of 8, so I have to draw 4 more. I'm going to start on the peripheral atoms, but I'm not going to put them around hydrogen. Why? Because hydrogen is satisfied once it has the 1s2 full. That's the only orbital that can accommodate electrons, at least at the ground state. So it's full and satisfied after you just have 2 electrons on it. It is a unique situation along with helium. Helium only has 2 electrons and it's stable because that's all you need in order to have this 1s orbital full. So the first energy level doesn't have any p orbitals. You don't have to fill those. You just have to fill the s orbital in the first energy level. So hydrogen is an exception to the octet rule. It is just a duet. It just needs 2. Does this hydrogen have 2? Yep, right here. You count these shared electrons for both hydrogen and sulfur. Does this hydrogen have 2? Yep, it has those 2 right there. That's all it needs. Sulfur, though, needs 8. So I need to draw my 4 more. Where am I going to put them? Around the central atom. And I'm going to, you can put them anywhere, but I know they're kind of going to spread out. So I'm going to draw it so that they're spread out. I'm drawing them in 90-degree formation here, but I know that's not going to be the case as we look at the VSEPR theory. So if I have 4 electron regions, 4 domains, 2 bonds, that automatically is going to lead to a particular shape. All I have to do is refer, it's just an easy transfer. Just translate it right to one of these 3D models here. 4 regions around the central atom, 2 bonds, 2 lone pairs, it's going to be bent. I would have my S here, and my hydrogen would look like that. I'm not going to draw the lone pairs because they're not really part of the structure. They're just pushing the angles down. They're taking up space up there. This is bent, and the angle between it, I think, was what, 104, something like that. 104.5. Okay. Let's move forward here, and I'm going to do the rest of these Lewis structures. I said I was going to do all the Lewis structures, and then I got caught up in the 3D drawing there. All right, pH 3. Let's go to our periodic table. So we have periodic table here. Our phosphorus is in the nitrogen group. It's got 5 valence electrons, and hydrogen each has 1. So that's 5 and 3 more. We're also going to have 8 valence electrons here. So our skeleton, I'm going to put P as central, bonded with a hydrogen each. And now I'm going to make sure I have all my 8 valence electrons represented. I have to have 8 valence electrons represented. 2, 4, 6. Each hydrogen is happy because they already have their duet, but I need 2 more electrons represented. Where are they going to go? Around that central atom. So now phosphorus is happy as well. 2, 4, 6, 8 around the phosphorus, 2 around each hydrogen, and that is our Lewis structure. I then just refer to my table. 3 bonds, 1 lone pair, pyramidal, looks like this. This is our P with my lone pair. and 107 or something like that. Okay. Yep. I guess it makes more sense to go ahead and continue with the 3D drawing because it kind of leads into that anyway. So I take back what I said before about drawing all the Lewis structures. Sorry. Carbon and chlorine. Let's count up our total valence electrons. Carbon here, 4. Chlorine is in the halogen group, 7 each. 7 each. So let's look at this. 4 plus 3, carbon for the 4 for the carbon, and then 4 times 7. So we're going to have a total here, 28 and 4. We're going to have 32 electrons represented. We have to have 32 electrons. Let's draw our skeleton structure. Carbon in the middle, bonded to each of the chlorines. With these 4 bonds, I've got 2 times 4. I've got 2, 4, 6, 8 electrons represented. I need a total of 32, so I'm going to need 24 more. 24 more. Let's start on the outside. 2, 4, 6. This chlorine is happy because it's got 8, counting that bond. 8, 10, 12. This chlorine's happy because it's got 8 around it. 14, 16, 18, 20, 22, and 24. Everybody's happy. Chlorine's happy, it's got 8. This chlorine's happy, it's got 8. Carbon is happy because it has 8. Everybody's got an octet. Happy, happy, happy. Stable. Compound makes everything more stable. Okay? So, as a result here, what shape are we going to have? We just refer to our table. Anytime you've got 4 bonds, tetrahedral, with an angle of 109.5. Okay? Oops, a little more angle there. Tetrahedral. And the last one. Carbon has 4. Sulfur's in the oxygen group. We've got 2 there. So 2 times 6. So we've got a total of 12 and 4 more. We're going to have 16 valence electrons represented. Put carbon in the middle. Skeleton structure. There you go. Now I have to make sure that I have drawn now 2 bonds which represent 4 total electrons. I need a total of 16, so I need 12 more. Let's start on the outside. 2, 4, 6, 7, 8, 9, 10, 11, 12. Interesting. Let's see what the deal is here. Does sulfur have an octet? Yes. This sulfur? Yes. Does carbon have an octet? You have to make sure at the end of your Lewis structure that everybody has an octet. There are exceptions. Usually the exceptions appear with the central atom, but for us, we're just going to focus on the main rule here. Everybody's got an octet except for hydrogen. Hydrogen only needs a duet. So let's look at this carbon. Oh, carbon is not happy. Carbon only has 4 electrons around it. 2 bonds means 4 electrons. What are we going to do? Well, as a result, carbon says, hey, sulfurs, you guys are not sharing enough. You need to share more than what you're sharing. So what they end up doing is these sulfurs both agree to share more until carbon has an octet as well. Remember, shared electrons count for both atoms that are sharing those electrons. So carbon and sulfur. So this sulfur on the right says, okay, I'll give you another pair. That results in 2 pairs of shared electrons. That's a double bond right there. So this sulfur has only 2 pairs of lone electrons. 2 lone pairs. Before it had 3, but it decides to share 1, and that gives carbon now 2, 3, 4, 4, 5, 6, if you look at the sulfur on the left. But that's still not enough. So the sulfur on the left says, okay, I'll do my job here too, and I'll give you another pair of electrons. So now carbon has 2 double bonds on either side. Everybody now has their octet. So that's how you determine if there are multiple bonds. If the central atom does not have its octet, then these peripheral atoms have to share more, contribute more to the central atom, resulting in multiple bonds. This now, is everybody happy? Yes, sulfur's got 8 around it. Sulfur's got 8. Carbon's got 8 because each double bond results in 2 pairs. So you've got a double bond and a double bond. This is still only 2 regions though. 1 electron region, another electron region. That results in linear, and linear has 180 degrees between the bonds. Okay? All right. Let's look at our extension questions here. O3 is not a linear molecule. Actually, it is bent with an angle that is a little less than 120. Draw the Lewis structure for ozone. Okay, ozone, O3. As we look at O3, again, let's go through these steps for the Lewis structure. It's helpful to repeat this. We have 3 oxygens. Each oxygen has 6 valence electrons. So 18. Okay? And what's going to be the central atom? Well, we only have oxygen, so let's just, put an oxygen here, bond it with the other 2 oxygens, like that. Skeleton structure again, draw it any way you want to, as long as you have the central atom and the other peripheral atoms around it. We've got a bond between those, so I have 4 electrons now drawn. 2 bonds, 4 electrons, 2 and 2. So I need to draw 14 more. Let's start on the outside electrons, and then we finish on the central atom. Sorry, the outside atoms, we finish on the central atom. Draw the Lewis structure here. 14 in pairs, 2, 4, 6. The bond makes it 8. 8, 10, 12. And then I need 2 more, so I'm going to put it here. Okay? Now let's check. Octet. Is everybody happy? Does everybody have an octet? This oxygen on the left, yes. 2, 4, 6, 8. This oxygen on the right, 2, 4, 6, 8. The oxygen in the middle, 2, 4, 6. Not happy. Okay? So, ozone has a bent shape instead of a linear shape. Why? Because this lone pair is going to push these bonds down. Okay? As we anticipate, this lone pair takes up more space. So, it's going to push them down and cause a bent shape. But there's a little bit of a twist here. That's why these are extension questions, right? This central atom here only has 6 electrons around it. It wants 8. So somebody's got to share more. You cannot just share 1 electron. These electrons are always in pairs. So you would think, well, each electron could share 1, because you kind of want to distribute it equally since you've got oxygen on both sides. So they're going to share in the same manner, okay? So the oxygen on the right says, okay, I'll share a pair. So we take this pair right here, we take it away from the oxygen on the right, we make another bond, okay? But you could have easily also said, well, what if the oxygen on the left decided to share a pair? Okay, let's reverse that. Give the oxygen on the right back his lone pair, eliminate this double bond, and create the double bond on the left with the oxygen on the left. Yes, you could do that as well. We have to remember that these electrons are not fixed necessarily in place. There are regions where we are pretty much guaranteed to find them, but they are able to kind of be mobile. We draw them as localized electrons, meaning they are in certain localized regions, but they can move around here. So really, what we have is we've got the bent shape, oxygen, because we've got this lone pair up here, and then this double bond, here I'll draw these lone pairs here. This double bond could be on either side. So you could draw the double bond here, or you could draw the double bond on the other side. Either one would be fine. So I'm going to show that either one of these are equal. Now this is called resonance, by the way. Resonance just means there's multiple Lewis structures that could be drawn. Either one is perfectly fine. And in actuality, you have 2, 4, 6 electrons spread across 2 bonds. Okay? We're limited to drawing them as pairs, but in essence what you have is you've got 6 electrons spread across these 2 bonds, and they really kind of spread themselves out equally as they do so, but we are limited in our drawing, in our model, to draw them either between the oxygen on the right or the oxygen on the left. Either one is fine, so sometimes we draw them both, put a little double arrow between them, and realize that either one works, and that's what is referred to as resonance. Okay? So we get this bent shape because of the lone pair, but also it's a little less than 120 because of this resonance effect here, because you've got these possible different arrangements. Okay? So that's just a little something extra, something called resonance, when you've got multiple Lewis structures that can result in the molecule. What you need to focus on from this video is being able to draw the Lewis structure given a formula, know the steps in drawing the Lewis structure, and then from that Lewis structure, realizing how many electron domains there are, how many are of them involved in bonding, and how many are lone pairs, being able, using a table, okay, if you want to memorize it, great, but if you had a table, you then should be able to refer to that table and determine what the three-dimensional shape would be, and keep in mind the angle between the bonds then. Okay? Very powerful, and kind of enriches your experience with chemistry, because chemistry is hard to visualize. It's hard to see because we're working with particles that you can't even see. So now we're able to actually kind of see what's happening at the molecular level, which is kind of exciting. All right, I hope this was helpful, and we will see you in the next video.